All right, we're going to go through and do the next section, which is called integration by parts. So before we get there, just a couple warm-up problems. If you want to kind of try these without me, like kind of on your own here, you can pause this if you want. But we are going to look at some old integrals and then get some new ones ready. So first one, give you a chance if you want to pause this and do it, because I'm getting ready to do it here in a second. When you look at this one and you have to establish your u has to be the natural log, because it's the only way we can integrate something that has natural log is to let u actually be it. And then the derivative is the du over u, so the derivative of 2x over 2x, or in other words, 1 over x. And you actually have 1 over x in your original integral. That's why we have this x down here. So we want to figure out what's being done to the natural log of x. Well, it's just there. It's just a u du, u the first du. So you get u to the second over 2. So you end up with the natural log of 2x to the second. You can put it in parentheses and square it, or you can put the 2 after the n plus c. Second one is an algebraic technique. This is going to be a split up type of problem where you're going to pretzel it here and you're going to pretzel it here. First part of your pretzel is going to be 2x over x squared plus 4, and then 3 over x squared plus 4. This is just a regular u sub. U is the bottom, du is the top. You're going to look and see that you already have the 2x there, so there's no adjustment. So this is a perfect du over u. So you're going to get the natural log of x squared plus 4. The absolute value is kind of unnecessary. This one, you can't do that because we don't have an x on the top. We just have a number. So this is actually an arctangent. U is x, du is dx, or just 1. A is 2. So we end up with plus 1 over a, 1 over 2, arctangent of x over 2 plus c. All right, so into the new material. So what we're doing now is we're doing a section called integration by parts. So we've gone through and talked about different ways we can integrate. We've got u sub, we've got trig, we've got inverse trig, algebraic techniques. Well, now we get to what's considered an advanced technique of integration. So something beyond what we did in Calc 1 and moving to Calc 2. So here's what we're looking for. Integration by parts is called that because the actual integral is made up of parts. It's always a product. So you're going to see the product of something like x's with natural log, x's and e's, x's and trig, e's and trig, e's and natural log. So some combination of functions. We call them algebraic functions if they're like x's. We call them transcendental functions if they're things like e or trig or natural log. So you have this combination of two functions being multiplied together that aren't really related in any way. Now, this is something that you would always want to try and see if you can do regular u sub before you do this. You don't want to jump into integration by parts if you don't have to, but this is kind of like that next level. So here's how the formula works. This is a formula that you just need to know. And to be honest, when I practice this is a formula I just kind of write down, or I have like a screenshot next to me, and I look at this formula constantly to the point where I start getting comfort with and I don't have to look at it anymore. So when you have this and you have your original integral, we need one of the parts of the original integral to be the u part. So looking at these up here, we need one part of it, either x or natural log, to be the u, and then we need one part that needs to be the dv. So once we establish what our u is, and we're going to talk more about how do you know which one's which, like I don't want you blindly trying things and taking up too much time. Once you figure out what u is, then you have to derive it to get du. That's what du represents, derivative of u. Once you know what dv is, you're actually integrating to get back to v. So you're kind of going forwards with the u and backwards with the dv. Once you do that, then you're putting everything into this formula. You'll have your u, your v, and then minus the integral of the v and the du. And I know it sounds crazy complicated, but I promise when you put it into practice, it's not as bad as it sounds. So some basic guidelines, and we'll get into more concrete later. Basic guidelines is you often want your dv piece to be the most complicated piece that you know how to integrate. So something like a trig can be a complicated piece, but if you know the integral of trig, then you can work with it. And then your u should be something that the more you derive it, the easier you get. Often your u is x's, because the more I derive like x cubed, for example, it becomes 3x squared, and then it becomes 6x, and it gets simpler the more you derive. There's always dx as part of your integral. It's always going to be part of the dv piece. I often forget to write it. I will show you one where actually writing is important, but for the most part, it doesn't do much. Here's kind of a little bit list to go through. Like this is the checklist of how you do these. Figure out what's what. What are your parts? And again, I'll give you some hard and fast rules so you're not searching. Figure out then what the du and the v are, put it into the formula, and then integrate the last piece. So we're going to go through and do 6 examples of this so you get to see a little bit of everything before we get into ones that maybe have some different steps. So this first one. So one of your parts is x, one of your parts is natural log. We have a rule that has said that anytime natural log is part of your integral, it has to be the u. That does not change in Calc 2. Your u has to be natural log of x, which means your dv is your x. dx, again, is part of it. I often don't write it. We'll talk as we go through when it would be necessary to write it. Once I have that, then I want to go underneath each part and write down what's the derivative of the natural log of x. Well, that's 1 over x. And then over here, what's the integral of x? Well, that's x squared over 2. Then I always put it in this order. I'm totally a creature of habit. I always have my u with my du under it and my dv with my v under it. Now I'm going to go back to the formula. So the formula is, once I have my parts, it is going to be u times v. So these two are going to multiply together. So I'm going to have an x squared over 2 natural log of x. You can write it in any order. It's being multiplied. Minus the integral of your v and du together. So minus the integral of these two multiplied together. Now, when I multiply those together, they actually get a little simpler. This x here will cancel with one of the x's here. So you're left with x over 2. And again, it's an integral. I'm always going to put the dx at the end. If you don't, it's not a big deal. Your last step is to integrate this. So my integral of that, so I've got x squared over 2 natural log of x. That part's done. Once you write it, you don't have to do anything else with it. The integral of x squared over 2 would be power 1 greater, so it would be x to the second power, divided by 2, but it's already divided by 2, so it's going to be divided by 4. So that's how it works. Again, I know that kind of sounds like a lot of stuff going on. Practice definitely helps, but that's the process that you're going through. So that's what's going to happen anytime you have a natural log and an x combined as part of your integral. Second one is, what do you do if it's an x and a trig? If it's x's and trig, you're going to want u to be your x's because x gets really simple when I derive it. And you're going to want your dv to be the trig function. Because again, trig function is more complicated, but we know how to integrate sine. So underneath u, you're going to put the derivative of x, which is just dx, or you could just write a 1. And then under the dv, you're going to integrate sine. Now, the integral of sine is an integral you should know or need to think back. It is cosine. However, because it's not just x, it's 3x, you will have a 1/3 adjustment. So it's going to be negative 1/3 cosine 3x. So negative is because the integral of sine is negative cosine, and then the 1/3 is the adjustment because the angle is 3x. So then again, to my formula, I'm going to multiply these two together. So I'm going to have a negative x over 3 cosine 3x, and then minus the integral of these two multiplied together. Well, there's already a negative here, so that negative is going to cancel with the negative that's out front. So I'm going to make that a positive, and I'm going to have a 1/3 cosine 3x. This is something I need to integrate. Now, the integral of cosine is positive sine, but there's still going to be an adjustment. Again, that angle causes an issue. So if I adjust it, I would do a 1/3 adjustment. There's already a 1/3 adjustment. So this is what my answer is going to look like. I'm going to have negative x over 3 cosine 3x plus, because the integral of cosine is positive, 1/9 sine 3x plus c. And again, these get kind of long. You'll often see on the AP test, they don't give you many of them. Even like an assignment, I'm not going to give you many of them. The other thing that's challenging about it is you don't really want to, I wouldn't ask you to then derive this and see if you get what you started with, because while you should, it takes a lot of algebra to get there. So let me talk a little bit about e's and x's. So anytime it has e's and x's, this is probably the most common combination that you'll see on an AP test, but it's also, in my mind, the easiest combination you'll see on it. Anytime you have it with x's and e's, you want your x to be your u piece, and you want your e to be your dv piece. And that will be true for any combination of x's and e's. Again, this is looking at ones that you couldn't do just regular u sub, which would be ideal. Derivative of x is just 1 or dx, so you can put a 1 or you can put 1 dx. integral of e is itself. However, there is an adjustment because of that exponent. So again, when you derive that exponent, you get -2. So you're going to have a -1/2 adjustment with my e to the -2x. Then I'm going to line it up. So these two will multiply together. So I'm going to have a -x over 2e to the -2x minus the integral of these two multiplied together, which is already negative. So that's going to make that a positive. So I'm going to have 1/2 e to the -2x. So then I'm going to integrate again. I get another -1/2 adjustment. So I'm going to end up with a -1/4 in front of my e to the -2x. And you can just write that as a minus sign, or you can put the plus negative like I did. And then this part doesn't change. I think that's where I will stop this video. So you get a chance now to kind of mess around with that. And then I'm going to get to some other cases and make another video.